Okay, my friends, today we're going to look at three different linear transformations defined by different matrices. And we're going to start with this one, a 2 by 2 matrix, -1, 0, 0, 1. Now, if my linear transformation is based on a 2 by 2 matrix, that means it's going from R2 to R2. And when I multiply this by any random vector xy, what happens here is I get negative xy. But what does that mean? It means that if I have a vector, a comma, x, a vector x, which is a comma b, and I multiply it by this chihuahua thing, I get here negative AB, but this is a reflection across the y-axis. So here's a linear transformation which winds up being a reflection across the y-axis. My next example is using this matrix to create a linear transformation. Again, this is a 3 by 3 matrix, which means the transformation is going from R3 to R3. Now, when I multiply a vector xyz by this matrix, I just get xy0. Now, what is that? That is what's going to be called a projection onto the xy plane, because if I have a vector, which is up here, xyz, this is the y-axis, the z-axis, the y-axis, the x-axis, this thing is sort of going diagonally like up in space. And now when I multiply xyz times my matrix A, I get xy0, which is a point directly underneath this original point, and it's on the xy plane. So it's called a projection onto the xy plane. If I would have an entire curve or entire whatever up here, up in space, and I multiply it by this matrix, it wind up getting sort of like getting like the shadow of it, on the ground, so to speak. And now for my third, so the third in favor, and this is actually my favorite one. Here we're using the matrix cosine theta, negative sine theta, cosine theta, and it's a 2 by 2 matrix, so it's going from R2 to R2. This, believe it or not, is a rotation. In other words, if I multiply this matrix times a vector, I'm going to wind up, the result will be that vector rotated theta degrees counterclockwise. But let's see why that happens. So first I have my original xy, and it's just a random vector, so the angle here is alpha. And this here is a times xy, and I'm claiming that it's going to be an angle of theta. How do I know this? Well, if I take x comma y and put it into polar coordinates, x is r cosine alpha and y is r sine alpha. Now, if I do the matrix multiplication, so that's my xy replaced by r cosine alpha, r sine alpha. Now I do the matrix multiplication. I wind up getting r times this whole thing here. I could pull out the r, but if you notice what we have in here, those of you trigonometry buffs know that this is the formula for on top is the formula for the cosine of the sum of two angles, and that's the formula for the sine of the sum of two angles. So I can make that r times cosine alpha plus theta, and that's cosine alpha plus theta. But that is a times the vector xy. That's what this is. Because here's my new a, and that's alpha and theta, and pow. So this works. So this is a rotation. That's a projection. And that's a reflection. These are three kinds of cool, awesome linear transformations. I'm out.